When we picture a computer, we visualize physical hardware, silicon chips, memory tapes, and read-write heads executing code. Alan Turing formalized this mechanical metaphor in 1936 with his concept of the universal Turing machine. A universal Turing machine is a theoretical mathematical model of a computer that manipulates symbols on an infinite tape according to a finite table of rules. Modern mathematicians have sought to strip away these physical metaphors entirely. The objective is to discover the absolute lowest threshold of algebraic complexity required to sustain universal computation. In 1987, mathematician John Horton Conway introduced an esoteric programming language called FRACTRAN. FRACTRAN is a computational model that abandons the concept of a memory tape and explicit state tables, relying exclusively on the multiplicative structure of rational numbers. We can mathematically prove that a universal Turing machine requires nothing more than exactly 14 modular residue classes and 16 distinct primes. A modular residue class represents all possible remainders when dividing by a specific integer, while distinct primes are unique, indivisible numbers. Universal computation is an inherent geometric property hiding inside the multiplicative structure of numbers themselves. A FRACTRAN program is defined entirely by a short, strictly ordered list of positive rational fractions. The system contains no external memory banks. The entire global state of the machine, its data and active instructions, is compressed into a single continuously updating positive integer, denoted as n. The execution loop itself is rigidly deterministic. At each step, the machine evaluates the list from the beginning and multiplies n by the very first fraction that produces a whole integer. This loop continues until it reaches a specific halting condition. If no fraction in the ordered list yields a whole integer when multiplied by the current state n, the program stops. This simple cascade of modular division checks replaces the complex logic gates, wiring, and physical memory registers of a modern central processing unit. How can a single raw integer possibly hold the complex memory of a computer program? The answer relies on the fundamental theorem of arithmetic. This theorem guarantees that every positive integer greater than 1 can be represented as a unique sequence of prime numbers. FRACTRAN utilizes these prime numbers as physical hardware bins. This animated diagram demonstrates how a single large integer, like 72, splits into its prime factorization of 2 cubed times 3 squared. The prime bases, 2, 3, 5, and 7, act as structural silos. Their exponents represent discrete blocks of data resting inside them. Specific primes are assigned exclusively to hold the program's logic states, while other distinct primes act as unbounded memory counters. Primes 2 and 3 act as data counters, while primes 5, 7, and 11 track the internal logic states. The raw macroscopic magnitude of the integer n is irrelevant to the computer. The FRACTRAN machine only reads and writes to the specific values of these discrete exponents. By treating prime aces as hardware and their exponents as mutable software, FRACTRAN mathematically solves the problem of an infinite memory tape. The rational fractions within the FRACTRAN list operate as atomic logic gates. Their sole function is to query and alter those prime exponents. As this animation shows, the denominator of the fraction executes the if condition. It drops down to check if the current integer n possesses enough prime exponents in its silos to be perfectly divided. The numerator executes the then operation. If the division succeeds, the fraction subtracts the denominator's exponent blocks from the silos and drops in new blocks based on the numerator. This introduces a strict mathematical boundary known as the square-free limit. A square-free number is an integer not divisible by any perfect square other than 1. To maintain absolute determinism and prevent chaotic exponent multiplication, the prime exponents inside these functional fractions can never be greater than 1. By subtracting the bottom and adding the top, pure arithmetic executes the exact same conditional branching logic as a silicon processor.
Locating the absolute minimum threshold of a FRACTRAN machine requires mapping its rules to the smallest known theoretical Turing machines. In 1967, computer scientist Marvin Minsky proved that a universal computer strictly requires exactly 2 unbounded memory counters. Therefore, the FRACTRAN system irrevocably requires exactly 2 data primes. This leaves the problem of finite state control. To prevent violating the square-free limit, the machine's states must be one-hot encoded. One-hot encoding is a structural method where exactly one distinct prime number is assigned to each individual machine state, ensuring no state exponent ever exceeds 1. Decades later, mathematician Ivan Collatz systematically optimized these universal register machines, driving the necessary logic down to an absolute minimum of exactly 14 operational instructions. We can now construct the spatial threshold mathematically. This visual matrix plots the required components. On the x-axis, we map 16 distinct prime numbers, 2 required for the data counters, plus 14 required for the one-hot encoded state logic. On the y-axis, 14 functional branching pathways connect these primes in a rigid, non-overlapping geometric web. Corax's 14 minimal rules map perfectly to 14 distinct functional branching paths. In modular arithmetic, these paths represent 14 distinct modular residue classes operating simultaneously to route the logic. Any arithmetic system possessing fewer than 14 distinct modular branches, or fewer than 16 primes, mathematically lacks the structural complexity to support Turing-complete logic without falling into unresolvable paradoxes. If computation is simply mathematical routing, why can't a simpler arithmetic map, like the famous Collatz conjecture, operating on just 2 classes using the rules 3x plus 1 and x over 2, compute universal algorithms? The answer lies in logarithmic drift. Logarithmic drift is an ergodic mathematical metric that calculates the average rate of exponential growth or decay in a sequence, dictating the system's long-term survival based purely on its fractional multipliers. The classical Collatz map has a negative contractive drift. This line chart tracks logarithmic drift. The sequence line for the Collatz map drops below the zero axis into the contractive zone, mathematically forcing integer orbits to shrink and collapse into tight repeating periodic cycles. Mathematicians like Terence Tao have analytically mapped these Collatz orbits, proving that contractive drift destroys information. As the integers shrink, the prime factor exponents that act as the machine's memory are physically erased by the descending modulus. The opposite extreme is an expansive drift, such as a 5x plus 1 map. Here, numbers uncontrollably explode to infinity, preventing the closed logical loops necessary to execute conditional computation. Between these extremes lies the Conway filter. The line representing the FRACTRAN threshold extends perfectly horizontally along the zero axis. To achieve Turing completeness, the machine must exist on this neutral drift manifold, precisely balancing expansive register increments with contractive state decrements. FRACTRAN's 14 residue class architecture is the simplest known mathematical structure capable of threading this exact neutral needle, preserving discrete information infinitely without decaying. The 14 fraction threshold represents the absolute mathematical boundary of decidability. This specific threshold marks the exact point where linear arithmetic transitions into universal computation. Below 14 fractions, arithmetic trajectories are completely predictable. At exactly 14 residue classes, arithmetic crosses into the chaotic domain of formal undecidability, governed by Rice's theorem. Rice's theorem is a proof stating that all non-trivial semantic properties of a computer program are mathematically undecidable. At this exact numeric threshold, simple multiplication becomes capable of expressing every unresolvable, infinite paradox within the universe of computable numbers. Computation exists as an inherent property of the integers themselves, operating regardless of silicon, electricity, or human intervention.